give this colloquium. So the topic of my talk is device-independent quantum cryptography. I hope if you are not familiar with the subject, by the end of the seminar you understand what is it about. So I will first start with the motivation, what exactly is device-independent and why we are interested in that. Then I will focus specifically on how this is, has many interesting implications for secure communication. And so finally I will talk a little bit about my latest research on this topic. Okay, so maybe when we think about cryptography, the first task that comes to our mind is that we want to perform secure communication. So here we have Alice and Bob. They would like to exchange a secret, very sensitive message, but there is an eavesdropper that could be intercepting this channel. And then a result which is now maybe quite old from the beginning of quantum information theory is that if we explore the properties of quantum systems, we can actually achieve this task with information theoretical security, which is like in contrast to what we have today for cryptography, which is based on computational assumptions. So the most important idea here is that Alice and Bob, they would like to have a secret key, which then they can use to achieve secure communication. And the main point that quantum cryptography plays a role is that we would encode these classical bits of the key using non-orthogonal states. Is this working? Yeah, okay. Using non-orthogonal states. And the idea is the following, because once we have non-orthogonal states, if I have an eavesdropper in the channel, if she would try to decode what was the bit that Alice sent to Bob, she needs to make a measurement, she needs to make an operation, and this is going to disturb the state. Exactly by the fact that we are exploring this idea of using states that are non-orthogonal. And okay, if the eavesdropper is in the channel, she tries to achieve some information. Alice and Bob, they can notice some Q-bar, some quantum bit error rate, which is basically the probability that they get mismatch on their bits. So if there was no eavesdropper, they would get perfectly correlated bits, but with the eavesdropper, they will observe this mismatch. We can see this as like a fact of no cloning, because Eve cannot clone the information, she has to disturb the information when she tries to get some information. Yes. Yes, so exactly. So yes, depends on. So here I'm talking about qubit states. So the bases here, 0, 1, are representing two orthogonal states, but I also have perpendicular bases, which is a superposition of 0 and 1, which here I'm representing by this plus or minus. Physically, this could be, for example, horizontal and vertical polarization, or 45 degrees, minus 45 degrees polarization. So both are states, all of these are qubit states, but they are not orthogonal, so there is not a single measurement that I do that can tell me for sure if I have 0 or plus. There is a measurement that can distinguish 0 or 1. Here, Alice is sending 1 qubit, but she can choose in which of these states, which nowadays we even call BB84 states, in which of these states she will prepare the qubit in. So they will repeat this protocol 10 to the 6 times. So each bit of the key would be 1 qubit. So the key is classical. So either she sends 0 by preparing one of these states, and similarly, Bob is going to make a measurement. He can only either measure the 0, 1 bases or the plus, minus base. So afterwards, they would check only the events where Alice prepared on the same basis as Bob that they can use for the key. So QKD, there is several post-processing steps which are completely classical, but the quantum part is Alice prepares something, Bob measures, and afterwards will come all this classical post-processing. Yes, you could send qubits, you could send continuous variable states, indeed. So here is the simplest QKD protocol that we have, but you need at least 2 non-orthogonal states. You can also use more bases and yes, I will come to bare states will be a little bit different, that it will be actually, Eve has the source and she sends one qubit to Alice and Bob. Both of them makes measurements. Here, Alice prepares and Bob measures. Okay. Good. So we have these non-orthogonal states. We can detect the eavesdropper, but the challenge of quantum cryptography is not just to detect the eavesdropper and throw away the protocol if there is an eavesdropper, because in practice, in reality, most of the times we don't really have an eavesdropper, but you have a noisy channel, which will always be the case, which will also cause these Q-bears. But here we are in the most adversarial scenario. Whatever I see a Q-bear, I say this is eavesdropper, and I will treat this as information that the eavesdropper has. So the BB84 protocol, so I mean, all of this that you asked is valid. I can do different QKD protocols. This specific list of points of numbers here are for the BB84 protocol, which is the most easy to implement, technologically developed of QKD protocols. So it's a very mature quantum technology, I would say. The main point is that it achieves information theoretical security as opposed to computational security. But now we can actually use post-processing techniques to tolerate quite a lot of Q-bears, so of this mismatch, up to 20% of channel in the noise. These protocols have been implemented lately with quite large key rates, so we are more or less, so I mean, this is a review from 2016. This is more or less the state of the art, except that people sometimes get higher key rates, but maybe lower distance, or they really make records of distance, but with a lower key rate. There is even, like nowadays, it's been explored quite a lot, implementations of QKD using satellites to transmit the quantum information. Okay, so okay, very nice. We have all of that. The problem is that all of these implementations of the BB84 protocol, it has some assumptions. It requires that we know very well what are the systems that we are preparing and what are the measurements that are being performed in the lab. So this is my picture, or theory picture of a lab. So here I want to depict that Alice and Bob, they need to know very well what's happening in the lab. And why is that? Because when that doesn't happen, the QKD protocol can be hacked. So at the same time that there is a lot of work in coming up with new protocols for, well, QKD and other cryptographic tasks, there are also a lot of people working on hacking these protocols. So here is just an example. This is Vadim Makarov, which is quite a famous physicist who works exactly on hacking many cryptographic protocols. And in this reveal, you can see like many of the sensitive points of the QKD protocols, which can really be hacked.
Sorry, another naive question.
Yes.
Say you're sending a qubit. Physically, is that an electron, or what you're sending?
I am sending a photon with a certain polarization. This is one example. Yeah. Or you can send a pulse, which and then the qubit is the time of arrival of the pulse. Yes, it can also be a qubit. This is the most easy to do experimentally, the most complicated to treat theoretically, because it's obviously not a qubit, it's a pulse, exactly. But there are techniques to handle like sending pulses and recovering a bit more, trying to avoid exactly these things here. Okay, so what was the point? I said the protocol had all that very nice features, but now it can be hacked. So here is usually what do we do in the security analysis. So usually we are given a state. For example, in the BB84, I said that Alice prepared one of that BB84 states. So there is a potential set of states that I'm trying to prepare on my implementation. And then I estimate some parameters, for example, the Q-bear, or some other parameter depending on the specific implementation that I'm doing. Now, this is the most important point for the security proof, is that how we model the eavesdropper. And the way we model the eavesdropper in a quantum system is by giving her the purification. So this is a purification of whatever state Alice and Bob had. And maybe this is the crucial point that gives us information theoretical security, because this is the most, from principles of quantum mechanics, this is the maximum information that the eavesdropper can have. So any other correlation that she can have with the system can be obtained by applying operations on her part of the purification of the system. So purification means, can I write here? So, okay, so I have a quantum state, rho ABE. I can go also to the mixed state scenario. So in this case would be psi-psi. And a purification is such that if I trace out Eve on my psi-psi, I recover my quantum state rho AB. But this is a pure state, so it's a rank 1 state. A general extension would be any state rho ABE, such that if I trace the eavesdropper, I obtain my state. Any extension of the state rho AB can be obtained by only eavesdropper applying operations on her system. Okay, so good. So with that, we calculate the states that Alice and Bob have after they perform the measurements, or after Alice prepared and Bob performed the measurement. And then, okay, then I can compute the key rate. So this is the steps of a security proof that we normally do. So where is the problem? No, that I said the protocols were hacked. So the problems are exactly on these 2 points here, because the eavesdropper I modeled on the most general way possible. But the problem is, I said there was a set of potential states that Alice and Bob were preparing, either from assumptions from my experiment or from assumptions that I would like to prepare the states. And there is a set of measurements. And the problem is exactly of these hacking protocols is that either they tamper with the set of states or with the measurements that you are doing. And this, on the measurements, for example, is very sensitive. It can simply be shining a laser and making the detector blind. And then the detector is no longer measuring the 0, 1, or plus minus bases, but it's just clicking because you just input a laser there. So that is where we have problems in the security. The what? The hacker could be in the channel. So Alice was sending a pulse to the channel to get to Bob. So the hacker could be some intermediate station here that is maybe collecting the pulse that was sent to Alice and sending a different pulse to Bob. So if this pulse is much more intense than what was expected to come from Alice, it would blind the detector, for example. Or it could be, I mean, nowadays we would like to buy, there is, I don't know, ID Quanticky. I would like to buy a QKD setup from them. Who knows what is inside this box? Okay. Okay, so finally I get to what we call device independence, and it comes exactly to handle these 2 problems that I talked about. So the idea here is that, okay, I have a source that is sending states to Alice and Bob. They will make measurements, but in the device-independent scenario, so it doesn't depend on the devices. Now I don't have anymore my labs of Alice and Bob with the beam splitters, photodetectors. I have boxes, black boxes, which I say, okay, the black boxes has inputs and outputs. So inputs can mean I'm doing different experiments, but I'm not saying any assumptions about these experiments. And then there is the outputs. So basically, Alice and Bob, they repeat it several times. They collect the statistics. And I would like now to make a security proof that is based only on these statistics. So you see, it's black boxes. There is no modeling of inputs and outputs, no assumptions on the dimensions, if it's continuous variable, if it's qubits, nothing. So this is what we call device independence. We don't want to depend on what is the mechanism that the device is doing. So such type of very strong security proofs, they are possible in quantum mechanics. So this is like, I find it fundamentally very interesting that we can achieve such type of things. And they are exactly based on another very interesting feature of quantum mechanics, that is quantum non-locality. So quantum non-locality will be based on the violation of a Bell inequality. So just to if you have seen that this phenomena was actually what was awarded with the the experimental demonstrations of the violation of a Barrow inequality was the topic of the last Nobel Prize that was for Alain Aspect, John Clauser, and Anton Zeiliger, where basically this experiment was, this Nobel Prize was rewarding all the efforts along the last decades to show that a violation of a Barrow inequality is something that can happen in the nature. And here just maybe very short explanation of what is a Barrow inequality. So I said Alice and Bob, they will collect the statistics from their experiment and they will observe that they have correlations. If their correlations could be explained by some random variable that maybe we don't have access to, it's some degree of freedom that I'm not aware of, but you see here that once I know this random variable, Alice and Bob, they are not correlated because usually they will be far away, they will choose the inputs independently, and we wouldn't like to have like signaling violating general relativity or special relativity that there is information from the inputs of one of the parties flying to the other party. So actually this expression is saying, okay, all the correlations that they observe, they could only have been from some variable that we don't have information. In fact, so this is, here I just have probabilities, but it's a fact that actually these probabilities could even be deterministic. So once I know this lambda, I know exactly what is the value of A. So the randomness and the correlations that Alice and Bob observe is just by the fact that they don't know lambda. So this is what Barrow locality is about. And then, but the point of cryptography is, if I'm violating a Barrow inequality, it means that there is no such lambda that can explain my correlations like that. If there is no such lambda, there is no eavesdropper which could have, there is an eavesdropper, but there is no lambda for Eve to know. So if there was such a lambda, it could be, for example, a variable that actually the eavesdropper knows, so she could have access to the outputs of Alice and Bob. So the idea here is there is no such lambda, so there is no such lambda for Eve to know. Okay, so how does device independence then will play a role? So actually we now would like to have device-independent quantum key distribution. And for that, we can explore the simplest Barrow inequality that exists. So this is the CHSH inequality, where C here is from Clauser of the Nobel Prize and other collaborators. And okay, we would like to have security just based on the probability distribution of Alice and Bob, given the inputs. So the CHSH inequality is a scenario where I have my black boxes and Alice has two inputs, so she can either choose to do experiment 0 or 1. The same for Bob, and they get two outputs, so 0 or 1. So it looks like qubit, but I'm not making assumptions that it's a qubit. It's just the number of outputs that I have. And the CHSH inequality is just an expression of the probability distribution, so it's the sum of these correlators. And here they are called correlators because this is it's checking how much Alice and Bob have same outcomes minus different outcomes. So they have same outcomes, this correlator is 1. If it's completely random, the correlator is 0. Okay, so what happens for this inequality if I would have a deterministic strategy? So here is just an example. So suppose Alice and Bob, the boxes always output 0 no matter what is the input. So we have that all these correlators here are going to be 1, and then the value for this quantity beta here is going to be 2. And so this is one deterministic strategy. You can do this exercise for any other deterministic strategy you can think of, and you will always be below 2. So basically, this is our classical bound, so our local bound. So violating the CHSH inequality means doing an experiment and obtaining a value higher than 2 for this quantity. Okay, but yes, so why I'm talking about that, then quantum mechanics should bring something for this case. And in fact, if this probability distribution is obtained by Alice and Bob sharing a maximally entangled state, so a Bell pair, and then doing the following measurements. So whenever input of Alice is 0, she's measuring the Pauli Z basis. Input 1, she measures the Pauli X basis. Bob has input 0, he measures this mix of Z and X, and so on. And they check what are the correlators. They obtain the value to square root of 2, which, in fact, one can prove that this is the maximum that can be achieved by quantum mechanics. Even if I'm using infinite dimensional systems, for this inequality, this is the maximum. So good quantum mechanics violate this inequality, so we can try to use it for device-independent cryptography. Okay, so the figure of merit, so the quantities I'm interested in, so I'm not just interested in signal locality, I would like to have a secret key. So secret keys, at least on the asymptotic regime, they are related to how much uncertainty the eavesdropper has about Alice's outcome, minus how much correlations Alice and Bob have. Okay? So here is just the condition of von Neumann entropy, which is defined in this way. But they are both quantifying how much uncertainty. So, and the second term here, it appears because of the fact that even when I don't have an eavesdropper, or if I just have a little bit of noise in the channel, Alice and Bob will not have perfectly correlated bits. So we need to correct for that. And to correct for that, the minimum amount of information that has to be sent is exactly the conditional information of Alice's outcome and Bob's outcomes. And just a side remark, so this is the case if I would like to do quantum key distribution, so they want to observe a perfect key. But just by looking at the first entropy here, I can already do a much simpler task, which is randomness expansion. So they can also use this protocol to derive genuine randomness that we can actually obtain with quantum mechanics. And for this case, I can also think that Alice and Bob, they could be together, and they are both obtaining randomness from their joint outputs. Okay, so good. Now we have a route to have device independent, but I just want to remark what are the challenges then. So before I said, before we would have a set of states, we do the purification, we give the purification to the eavesdropper, and then the task is to calculate this entropy such that I can estimate my Q rate. But now the device-independent scenario, I have no assumptions about the internal working of the device. So I have no assumptions of what is the state and what is the measurement that is being performed. No assumptions on the dimension. So at the same time, and I want to calculate these entropic quantities, which are not linear quantities, so the problem is much more complicated. So we still need to improve on techniques. So here I'm mentioning some techniques. There is some numerical techniques that work on the space of probability distributions. They can give us bounds on such quantities, but usually these bounds are not tight, so they can be improved. So there is one quite old technique that doesn't give us a very good bound, and some more recent techniques which have the hope to give tight bounds, but they are numerically quite demanding. Okay, maybe just I want to do a remark why we would like tight bounds, because once we have tight bounds, we really have protocols with optimal rates. And I would like to show more or less where we are in terms of experiments and the parameters. So in a DIQKD protocol, using the CHSH inequality, I'm estimating the violation of the CHSH inequality and also some Q-bear that Alice and Bob needs to correct such that they have the same string. So this graph was from a paper of 2019 where we were evaluating what was the state of the art and can we have the IQKD implementation. Because we have implementations of BB84 protocols since quite many years, but the IQKD was still missing. And this was the black dots were examples of bell tests, some of them completely loophole-free or just detection loophole-free. Usually these ones here, they have very low Q-bears, but horrible violation. They are photonic experiments, and the other ones are ion traps, trapped atoms, trapped ions, or NV centers, or usually things that are not just the transmission of light exactly that is on our qubit. But the last year, like very remarkable results for the field of device-independent quantum cryptography was the first proof of principle demonstrations of these experiments, of the IQKD. And these first two experiments here I now plotted them here. You see that one, maybe before I go into that. So the black region means that I cannot have the IQKD. Yes, I have a violation of a baryon inequality. I estimate my Q bar, but this is not enough to obtain, some positive key rate here. And the green region means that, yes, I can have QKD, but these curves are showing how many rounds do I need in order to account for finite size effects and still have a positive key rate. Yeah. So if I have a violation, it means that the eavesdropper does not know, or because there is no lambda that determines the outcome of Alice and Bob. So it's the opposite. But it's not sufficient to have a violation, because first I have to correct for errors, and I have to try to estimate how much information the eavesdropper could have once I have a violation. So that's why here I start at 2, because below 2 there is no violation, so therefore no security. But here what this graph shows, even when I'm here, I have a violation, but I'm still on the red region because it's not sufficient to have asymptotic key rate. So I need to calculate these 2 entropies, and it's not, it's smaller than 0, so it doesn't. And the curves here are showing how many rounds would I need to actually achieve a key rate. So I don't know if it's possible to read, but here is 10 to the 6, 10 to the 7, 10 to the 8, and so on. So you see that this first experiment 1 is around 10 to the 6. They actually did the experiment until the very end, so they did all the steps of QKD, and they generated a secret key. This experiment 2, they would need 10 to the 8 rounds with trapped ions or trapped atoms. It's really not possible. They would take, I don't know, 10 years doing the experiment. So it's more like they show that they achieved enough parameters that are good enough. But on the other hand, the experimental platform was 400 meters away, and this one was in the lab, so it's only 8 meters or some of fiber. So both were recognized, so they were both in nature, but it's still like very proof of principle. This one was very interesting, so it was from the group of Pan in China. They made the experiment with photons. But with photons, there is no way that you come up to this region here. You are always like here because you have a lot of photon losses that there is no way to overcome. So they proposed a technique that you could potentially post-select the rounds. So in their case, it's hard to actually say which key rate they would have. And this technique is only secure if you have the assumption that all the rounds are the same. So the preparation and the eavesdropper attack, so you have an IID assumption, which is really not good in cryptography, but it was one of the first attempts to actually obtain something with photonic experiments. So this is quite also super interesting. Okay. Oof. Let's see how much I managed to talk about. Okay, so this is with CHSH inequalities, but we have so many other baryon inequalities with more inputs, more outputs that have been shown to be necessary to really prove non-locality of correlations of different quantum states. So can we use this baryon inequality? So my question is, okay, if I have other baryon inequalities, do I get better the IQKD protocols? Or do I get also device independent for other protocols that goes beyond QKD? So this is what I would like to talk about now. Yes? So, I mean, it has a practical interest because it would be really not hackable. It would be the most high level of security that you would have. At the moment, yes. So even, okay, QKD in general, people don't envision that at some point we'll just replace everything by QKD. It will be either hybrid, we will have classical and quantum. At the moment, I feel like this is more to the theoretical level. It's interesting to see what you can get. But, I mean, the experiments really go quite fast. So I wouldn't be surprised that at some point it's quite cheap to do such thing. Ooh, when? okay, so in 3 years, they managed to do a proof of principle implementation. I don't know, maybe like 20, 50 years, something like that. It will still be slow, so I don't think this is something we use for... No. And maybe like that, maybe people will focus on such a thing really for like very sensitive communication as well. But, okay, while people are trying, so these experiments, for example, to prove Bell violation, they are not being used nowadays necessarily for Bell violation, but they really advanced a lot long distance distribution of entanglement. So that's... Yes, yes, yes. No, that definitely yes. Yes, but just, yeah. Okay, so, yeah, so my vision now for maybe 100 years from now. So now we just have the first proof of principle demonstrations of the IQKD, but one day we will have a quantum network with several processors connected together. And okay, if we go beyond QKD, can we do such protocols in these networks? And now the first simpler task that we can go on going beyond this HSH scenario would be secure broadcast. So now I don't have only Alice and Bob, but she would like to send a secret communication to several users on a network at the same time. So of course she could first establish a key with Bob and then establish a key with Charlie and then broadcast her key to both of them. But in quantum mechanics, we have not only bipartite states, we also have multipartite states, and we have different structures of multipartite entanglement. So is there an advantage on this type of protocols? So this is the question that is asked here, especially in networks where I only have a central server that can only distribute a quantum state at a time. So it has been shown some time ago that actually, yes, you have an advantage if you use multipartite entanglement and already perform the protocol to establish a common key at the same time. And now another question is, okay, do we also have an advantage if we are talking about the IQKD? So this, maybe just to mention, this task is called conference key agreement, so not anymore just quantum key distribution of two parties, but they are all agreeing on a common key. Okay, if I would like to talk about device independence for conference key agreement, then I would need to look at a Bell inequality that has 3 or more parties, and then similarly, each of the parties have their set of inputs and set of outputs. So in this work now of some years ago, we actually showed that, yes, you can do that using a multipartite Bell inequality, and you do get an advantage again for these networks with bottlenecks. So the advantage increases with the number of parties, but unfortunately, the noise tolerance decreases as you increase the number of parties. So these Bell inequalities, they are less noise tolerant. For this case, we used an inequality where only 2 of the parties had 2 inputs, and all the other ones, they had only a single input, which was very similar to the CHSH inequality, which then we could calculate this entropic quantity that we needed, that in general is very difficult since you don't have assumptions about the dimension of the system. So now, more recently, we were looking, okay, let's take a look at other Bell inequalities to see if we get an advantage in general. So this MAPK inequality is a generalization. MAPK stands for the people who studied this family of inequalities, so as an n-partite inequality, and is the generalization of CHSH, where each of the parties has 2 inputs and 2 outputs. And this inequality is also like non-locality. It has a geometric interpretation. So the classical set is actually a polytope, and usually it's the Bell inequalities, they can be the facets of these polytopes. Bell inequality is anything that tells me separates quantum from classical, so not necessarily I need to look at facets, but this MAPK is a facet of the multipartite polytope. the parity CHSH inequality that I mentioned, and there was this other inequality that was introduced in a paper that was investigating exactly the task of conference key agreement, and it was conjectured that would be a very good inequality for this task. So in this works, we were exactly investigating this task. So how can we bound these entropies, and how can we apply these bounds for the applications to derive conference keys for device-independent conference key agreements, or just randomness expansion. So I would just like to mention a little bit about the proof ingredients. So how can we compute these entropic quantities, which are non-linear, very complicated ones, since I don't have even an assumption about the dimension of my system. So the trick here, so that was the same for the CHSH inequality, which the bound was known for quite some time, is the result that if I'm in a scenario where each of the parties have only 2 inputs and 2 outputs, there is one of Jordan's lemma, at least in the language of quantum information we call it Jordan's lemma, but maybe it's not the standard one that you talk about. But basically that says that the operators that describes my measurement, they can be Bell diagonalized in subspaces of dimension 2. So in cryptography, this means that, okay, then whatever realization that Alice and Bob are having, I don't know the dimension, but I can describe it as a direct sum of subspaces of dimension 2. So basically, I can restrict my analysis, so there is a little bit of a step to that, but I can restrict my analysis to just qubits and projective measurements. So I came from, okay, I want to estimate entropic quantities for a state which I don't even know the dimension, to now I can look at just qubits, give the purification to eavesdropper, and then do my analysis. Another step, because still here I have many parts, in the case here I have 3 parties, is actually to look at the state. We could simplify quite a lot the state by using the symmetries of the Bell inequalities. So some of the Bell inequalities, they were invariant if I flip some of the bits. And because of that, I can simply just look at the most general state that I need to take into account. If I write it in the G8Z basis, or the basis of maximally entangled states, they are basically almost diagonal, so except for one off-diagonal term. So in general, because of exploring a little bit more of these properties, there are some more intermediate results, but I think these are the 2 most important ingredients that we use in both of the works. We could derive analytical expressions, and expressions of which type. So here it's the entropy, the uncertainty that Eve has about Alice's outcome when she had input 0, and just as a function of the observed violation. And we can actually show that some of these bounds, they are actually tied by exhibiting a specific realization that achieve this bound. For the case of 2 inputs, analytical bounds are more difficult, so we can do that for the family of Mabi-K Bell inequalities. But for the other Bell inequalities, we obtain it over a numerical minimization by exploring also these simplifications of restricting to qubits and restricting to an almost JZ diagonal state. Okay, so finally, I can show some graphs just to comment a little bit. So if I'm looking only at a single party entropy, so here the entropy as a function of, not as a function of the violation. Here we looked at a specific noise model. So either if it's a tripartite inequality, my G8Z state undergoes some local depolarizing channel, or bipartite inequality, I just have a Bell pair that undergoes this depolarizing channel, and with that I can actually compute both parameters, the violation of the Bell inequality and the Q bears. So this graph here I'm showing as a function of the depolarization parameter. So here the pink one is a bit of a variation of CHSH inequality, where you can put some weights on the inequality, and indeed this is the one that leads to the highest entropy so far. So it's really very difficult. Well, no one showed any result yet where you really improve noise tolerance and really the entropy, single party entropy that you obtain from the CHSH inequality. as I mentioned, so the map K here, which was a facet of the multipartite polytope, is the one that leads to the worst result. And this inequality, it also has some interesting bound, so which is this red line here, that if the state is below this threshold, it's not a genuine multipartite entangled state, and I need to have genuine multipartite entanglement to, I will talk in a moment what exactly is that, but it's the highest form of correlations that I can have in multipartite entanglement. Yes. I would like to have a highest, but I want to minimize over all realizations that lead to a Bell violation that I observe. So this is to say that it's really the worst case scenario. So I don't know which implementation I have, so I have to minimize over all of them. So I'm minimizing. Yeah, so here the HOTS, which was the third one that I talked about. Okay, I will not go back there. It leads to the best noise tolerance and highest entropy. But in a moment, I will show the graph of actually the key rate. So this is just the entropy, the uncertainty of the eavesdropper. So we see that bipartite is the best. But when I look at the two-party entropy, which is a very good quantity for just randomness generation, then I see that I have a huge advantage of using this facet inequality, both in terms of the amount of randomness that I get, and also in terms of the noise tolerance, because my P can go even up to 0.8 here. Okay, so I mentioned about this, what is this GME? So just to say, so if I have just bipartite states, either they are entangled or not, but when we go to the multipartite scenario, we start to have many structures of entanglement. So I can have that my state is separable across a partition. So Alice and Bob here have entanglement, but Charlie is not entangled. And I can have some combination like that of states that are separable, but because of this combination, the total state here is not separable across any partition. And I can have a combination of states that are separable with respect to all partitions, but they are still called biseparable. So if my state cannot be written like that, then finally I have genuine multipartite entanglement. So this is the case for the GHZ state, is a genuine multipartite entangled state, because I cannot decompose it like that. And these Bell inequalities that we are looking at, there is a threshold of the Bell inequality that if I violate it more than the certain value, I'm sure that my state has to be genuine multipartite entangled. So now it's the plot of the key rate. So we can see that even though the entropy of the asymmetric CHSH inequality was better, but now because I'm considering a network with bottleneck and I need to repeat the experiment 2 times to establish a key between Alice and Bob and Alice and Charlie, then I lose again with respect to using a multipartite Bell inequality. So here you can see that the asymptotic rate is lower, the noise tolerance is still better, and we have this HOTS inequality was the best for conference key agreement. And now maybe just quickly here, I could have a violation of this HOTS inequality even without a GME state. But when I look at the key, it's not shown here, but all this value of P can only be achieved by a genuine multipartite entangled state. So this is a question that we can ask, is this type of very strong multipartite entanglement necessary for device-independent conference key agreement? Previously, we have shown that for a standard conference key agreement with assumptions on the devices, this was not necessary. So it's still an open question about the resource. And now on the side here, we are showing the rates of randomness expansion. This gamma here is, most of the times I use the rounds, here it's not written, the input 0, 0 for the randomness, and the other ones I use only a few times to really test for the value of the Bell inequality. So this is the gamma parameter. And this CHSH with no spot checking was the best randomness expansion protocol so far, where they managed to reuse the randomness that used for the input. So I need to choose the inputs randomly, and then I will generate outputs that are random. And in this case, they make a reuse of the randomness, and we can see that this multipartite Bell inequality even performs better than this case. Okay. So maybe I have final moments. I would like to still talk about the use of device independence for a different protocol. So far we were talking about just secure communication, secure broadcast, but actually quantum cryptography goes much beyond QKD. So we have many different tasks that were proposed and investigated so far. So they either are classical tasks that have the security improved by quantum mechanics, or even like completely new functionalities that are quantum functionalities. And in this task that I was discussing so far, of secure communication, we had protocols with different levels of trustedness. So I started talking about the BB84 protocol, where Alice and Bob needed to trust the source or the measurement devices. And then I ended up talking about the DI-QKD, where it's the most adversarial level, where they don't have any trust on their measurement devices. But in all these protocols, the parties, they were interested in acting honestly. They wanted to establish this secret key. But there are some tasks where actually there is an interest that the parties would misbehave during the protocol. So usually are types of tasks where some information is actually hidden from the participants. So here I have two examples. I have the example of secret sharing, where Alice would like to share this quantum state between all the 4 nodes in the network in such a way that if 2 of them come together, they shouldn't be able to recover the state. All of them have to come together to recover the state. So in this case, these 2 parties here, they could try to do something to try to find out what is the state. On this side, we have anonymous communication. The idea here is that I have a network with several participants. Everyone has to collaborate for a sender to send a quantum state to a receiver. And at the end of the protocol, we would like that no one is aware of who is sending this information. So maybe like this is scenarios of whistleblower or things that the parties that are communicating, the identity is very sensitive. And they wouldn't like it to be revealed. How much time should I have? About 10 minutes? Okay. So how can we verify states in a network in the presence of dishonest parties? So this task was first investigated in the device-dependent scenario, so where we know the devices, and basically the figure of merit that people were looking, so they wanted to certify the JZ state, and basically they were looking at the distance of the state that was actually distributed by the source, allowing for a joint operation on the dishonest parties, because we cannot exclude that they are actually acting all together. And then the idea was, okay, how can I bound this quantity? So this was the figure of merit, and such, let's say, such condition is sufficient to lift, for example, the anonymous communication, so this protocol that I just draw here. So there is a protocol to perform this task using the GZ state that initially we needed to trust the source, to assume that the source was distributing the GZ state. And now such type of conditions, they can ensure that I actually can perform this protocol and I do not need to trust the source. So you can see that this paper is from 2012, and now more recently there was again interest on this type of verification, and basically that's because nowadays the experiments are being able to distribute multipartite entanglement. So now people are able to explore such protocols again. So later there is maybe a more weaker condition. I can look at what is the fidelity with the distributed state with the JZ state, and such condition ensure that actually I had a genuine multipartite entanglement was distributed between the nodes in the network, and lately it was also extended to graph states. And now my question is, okay, can we look at the most adversarial scenario of state certification? That would be, I have dishonest parties and they don't have to make any assumptions about the working of their devices. So I will just talk in a few minutes about this latest works that was in collaboration with Flavio Baccari, where we introduced a framework for device-independent entanglement verification with dishonest parties. And device independence, we need a Bell inequality, and now I need a Bell inequality that I did not talk about before. And this is the family of Svetlishny inequalities. So again, all the results I'm presenting today, they are for Bell inequalities with 2 inputs and 2 outputs. So we have n parties, 2 inputs and 2 outputs. And this Bell inequality is similar to the others. I have this correlator. So the correlator is basically, I look at the product of the outputs or the parity of the outputs, and I check parity 0 minus the parity being 1. So generalization of the correlators I presented before to n parties. And okay, my Bell inequality has some coefficients and includes correlators of all the parties. Maybe what is interesting to know about this Bell inequality, so it has a local bound and it's violated by quantum mechanics, so I also have my quantum bound. But this is a very strong Bell inequality because basically to violate the classical bound, I should not be able to write my inequality of, as a combination of correlated states of this form. And what I'm saying here, so in the bipartite case, I just had Alice and Bob. Here, I'm allowing that I have a partition of my system. They have an arbitrary distribution, which could be signaling, could be a joint distribution. I'm not making any assumptions. I just say that, okay, this is uncorrelated with the other partition. Maybe I can go like this. So this is a bit similar to the definition of genuine multipartite entanglement. So actually, this inequality was said that it witnesses genuine multipartite non-locality. So genuine multipartite non-locality because I'm saying my distribution cannot even be written as a combination of distributions that are uncorrelated only among partitions. This is a quite strong, and nowadays people were not using this definition of non-locality so much because it leads to inconsistencies when we are talking about the framework of general probability theories and not about quantum mechanics exactly. And I want to make operations just at the level of probabilities. But you will see that actually this is exactly the definition of genuine multipartite non-locality that we would like for our scenario with dishonest parties, because the dishonest parts could actually be acting together to perform an operation of this form. Okay, so I have my network, and maybe I have a set of dishonest parties. So just to model the honest parties, they would be doing a measurement, which here would be just the observable. They have a measurement related to the outcome 0, a measurement related to the outcome 1, and the way that we model the dishonest parties is to say, okay, they should be doing individual measurements, but they could actually be doing a completely global measurement involving all the inputs and outputs. Maybe in the interest of time, I will skip this part, because I would like to talk about self-testing. So I talked about the violation of a Bell inequality, what it means. It means that we don't have that decomposition, that the correlations can be explained by a joint hidden variable, so some extra degree of freedom. But there is something even stronger that we can obtain with non-locality, that people show that when we have a violation of some Bell inequalities, when I'm at the maximum violation, I can actually talk about what is the structure of the state and the measurements. In particular, for the CHSH inequality, when I have the maximum violation, the only state I could have is actually the Bell pair. I could not obtain maximum violation of the CHSH inequality having another quantum state. Up to some local isometries, of course, we always have this extra degree of freedom. So this is the type of statements that self-testing does. And here we introduce the concept of self-testing with dishonest parties. So the idea here is I would have a probability distribution that maximally violates some Bell inequality, and I want to have the same strong guarantee. So I want to say, okay, any quantum state that I have that led to this probability distribution, it can be transformed to my target state by only up to some isometry, some channels, but here I allow the dishonest parts to have this global channel. Okay, so I don't know which state I had. I obtained maximum violation. I'm sure that there is some component of this target state in my system. And the same guarantees can be actually being done for the measurements. I can also say, okay, my measurements are actually equivalent up to local isometries to Pauli X, Pauli Z, and so on. So what we showed that using this Svetlishyn inequality, that the maximum violation of the Svetlishyn inequality can self-test that I actually have a k-partite GZ state between the set of honest parties and the group of dishonest parties. And because I have this Freedom operator on the dishonest set, I could actually bring my state to the n-partite GZ state. So with that, I can say if I observe a maximum violation of the n-partite Svetlishyn inequality, I'm certifying the n-partite GZ state in this device-independent way in a network where I have a subset of parties that are dishonest. I don't know who are these dishonest parties, but I can still have these strong guarantees. Similarly, I can also have some more noise robustness statements where I can look at the fidelity with the GZ state up to local isometries in the honest parties and these global isometries on the dishonest parties. And so in our paper, we relate this quantity to a previous quantity that, with the fidelity for, let me rephrase. We relate this quantity with dishonest parties with the fidelity for the case where we don't have dishonest parties. So this has been investigated in these references here, and then we derive a bound where I have the violation of my inequality and these two free parameters that can be determined by doing some optimizations. And we actually relate our quantity with dishonest parties with the same parameters for the case of no dishonest parts. And with that, we can also have such type of conditions that not only I know that I have a GZ state when I have the maximum violation, but I can also bound what is the fidelity with the GZ state when I don't have maximum violation. Okay, so finally I'm getting to the end. So my take-home message is, well, first that device independence is fundamentally very interesting, and maybe practically, well, we have to see, but we are really exploring fundamental aspects of quantum mechanics to bring the security to the most adversarial scenario that we can have. And what I wanted to present is that exploring different Barry inequalities can lead to better device-independent protocols or even to new device-independent protocols. So this last part, I was talking about a task, potential applications to a task that is not just secure communication, but a more complex task. So I focused on exactly looking at the application of multipartite Barry inequalities for device-independent conference key agreement and device-independent randomness expansion. And finally, I talked about self-testing with dishonest parties and the potential application for more complicated network protocols. Just some outlook, some things that I briefly mentioned that so we know how to explore some Barry inequalities and obtain device-independent, device-independent guarantees for cryptographic protocols, but there is still a lot to be understood about what are actually the resources that are necessary. So we know that entanglement is necessary for having quantum key distribution. But now here we were exploring multipartite scenario. We don't know if genuine multipartite entanglement is actually a necessary feature or not. For the last part, I talked about this strong definition of genuine multipartite non-locality. So is it really necessary for having this very strong type of state certification? So in this topic, at the same time that we explore protocols for specific Barry inequalities, we can also ask a lot of fundamental questions about what are the resources that are necessary. just to mention for the last part that I was talking about state certification for applications of protocols, for example, anonymous communication. My motivation actually to start this work was basically to see if we could certify other tasks or other classes of states. So far, all the protocols I talked about, they are the GHZ state, which is states that are stabilized states. But actually, the W state is another class of multipartite entangled state that has been shown to be quite interesting to lead to more noise tolerance for protocols, but it's not a stabilized state. So there is no way to extend directly the techniques that existed before of state certification. But it does violate the Barry inequality. So another interesting question for the future is, can we extend such type of certification for other classes of quantum states? And finally, I talked about state certification, but of course, I would like to talk about security of this protocol, but there is a huge gap for just classifying and characterizing the quantum state that I have, to the point that really formalizing a security proof that is robust to noise using this certification protocol. So this is maybe even more in the future, because just direct applications of the results that we have so far, yes, it leads to security. I don't need to trust the source that is distributing the state, but it's really not noise robust. So that is really a challenge in cryptography. And yes, with that, I would like to thank you.
Well, thanks for the talk. I would like to ask you if we need fully working quantum computers for this kind of network protocols to work. It doesn't look like so for me, because we're just shooting photons at a certain polarization and then making measurements, but maybe I missed something.
Yeah, no, we don't need. So quantum communication is, let's say, much simpler than having quantum computers, because usually we just need to send and detect. Even the BB-84 that I started, you don't even need entanglement. Alice can just prepare and Bob measure, but when we are talking about Barry inequalities, then we need entanglement distribution. So this is the minimum level of the minimum level of resource that we need for this protocol here, for example, that I didn't talk about this protocol, but it would require entanglement measurements to do a teleportation, and for this part to correct for the teleported state. So it would require some quantum memory. But it's still, so let's say the most advanced here would be quantum memory, which is still much simpler than having a quantum computer working.
So in this last part, I just didn't understand, are you seeking to have the maximum violation, or is just a region where things are a little bit more interesting to?
No, so I mean, I would like to have results in general, so that's why there was this part of robust results. But such type of self-testing is really just for the maximum violation. Then the challenge is, yes, you can have a region around it where the guarantees are still valid. But let's say the self-testing is really more a fundamental thing, not to exactly with application.
I had a more general question. So maybe harder to answer. So we all do theory, so there's nothing wrong with doing theory, but are we learning something about quantum mechanics by doing this? Or what are we learning about quantum mechanics by doing this theory? So obviously it's possible applications, but is there some way to test quantum mechanics doing this, or is that?
I mean, to test quantum mechanics.
Quantum mechanics is a theory, right? Which eventually is going to be overturned into another theory. But is this useful for testing it?
Barry inequalities nowadays, in general, but it's an area that I don't work much, but even just Barry inequalities, or they call non-local games, is a specific set of Barry inequalities. I know that people are finding equivalence to A, C, D, F, T, duality, I don't know, such that if you violate this baryon inequality up to a certain amount, but it's really like recent work and it's not something that I work on, it would have some implications for this order conjecture. Here maybe, I mean, okay, here I'm talking about the final result of the applications, but the modeling of these problems, I find it quite interesting. How can we model? Because of all of this purification, so you really have to, I feel we explore a lot, like how are the quantum correlations, how they behave when we try to estimate these entropies, for example. So this is one step for calculating key rates, of course, but really we get quite many insights of how quantum correlations can behave. But testing quantum mechanics as opposed to other theories, maybe this is something interesting I can talk about. That so in general, the baryon locality scenario, we talk about these probability distributions. Anyway, we talk about the probability distributions, and we can remove quantum theory from that. I can say, now I look at the probability distribution space and ask about what delimits quantum theory as opposed to other theories, so generalized probability theory. But here, for quantum cryptography, you can see that I'm using baryon locality, but I'm assuming quantum mechanics. So in a sense, in this case, I'm not working on the testing, but I'm always assuming quantum mechanics for all these proofs. And in particular, there are results showing that if I don't assume, if I just assume non-signaling, that is one of the minimal conditions we can input on the probability distributions, you cannot have such type of classical post-processing and proof security of QKD. So, I mean, so some works that I do more in just baryon locality, then indeed, yes, there is a little bit more on the aspect of testing quantum mechanics, but not here.
Other question? Any other question? Okay, so let's thank Gláucia again for her nice talk.
Thank you.